Today, we are going to be working with clay soil, specifically brown clay soil, the most common type of clay soil in this area. Let's start with the sedimentation test. Well, we get clay soil, put it in a glass jar. It's already in a glass jar. We add water. And shake until everything is dissolved. Here we can see the different soil layer compositions. At the bottom we have sand and gravel. The next level is silt, and the last is clay. As we can tell, clay is on the smallest proportions, and it acts like a binder in the same way cement acts in a concrete mix. The more cement, the stronger the concrete is up to a point. Clay soil comes in many different combinations. What we have right here is what we normally find in the Monterrey area. But clay is also present in other forms. Diatomaceous clay. Diatomaceous clay is made from the skeletons of microscopic organisms. These organisms have lived on Earth for millions of years, and they can be found in various locations in varying quantities. This type of clay is also used to filter water because it doesn't shrink and is very porous, allowing water to pass through while trapping impurities, as well as in beer and wine filtration. Bentonite clay. Bentonite clay is found in different amounts across many areas. In places where there is high concentrations of bentonite clay, problems can happen when the houses are built in soils with bentonite. And after the ground dries up over the years, we can usually tell bentonite is present because the soil shrinks and settles unevenly, causing the floors to become uneven. I have seen places where I had to replace floor support piers because they had sunk by as much as 3 to 5 inches, which is really bad. It causes cracks in the walls and creates many other structural damages, leading to significant building damage. Bentonite clay is also used to seal ponds because it absorbs water and becomes impermeable. It's commonly used in the drilling industry as well, where it works as a lubricant and it helps flush out all the drill cuttings. Here we have a sample of bentonite clay that we soaked in water and then filled this cup with it. Over time, we let it dry, and now it has shrunk to about 1/5 of, or even less of its original volume. Going back to native clay soil, when we dig up clay soil in nature, it's usually very hard. But once it gets wet and start mixing around, whether by walking it or driving over it, or any kind of disturbance, when it dries, it becomes much harder. I mean, you really need a jackhammer or a drill to get through it. That happens because all the pores disappear and the clay compresses very tightly. That's one of the reasons plants have such a hard time growing in clay soil. In its natural state, clay has some porosity, but once we disturb it, it can become extremely compacted. When it gets wet, it doesn't allow air to reach the roots, so the roots practically drown. Then when it dries out, it becomes so hard that the roots can't penetrate it. That's why clay is very difficult to work with and very difficult for plants to grow in it. Let's take a look at what a professional soil analysis of this particular soil looks like. Right here, I have a soil analysis of this particular clay soil that was done at Midwest Laboratories. We will start with organic matter. In this particular sample, we have an organic matter content of 0.8%, which is very low. In this type of soil, we ideally should have between 5 and 10% organic matter content to make it suitable for gardening. Then we move on to phosphorus. There are two different types of phosphorus test. One is called the weak braid test, and the other is the strong braid test. They use different testing methods, but either way, with this clay soil, we can see that the phosphorus levels are very high for both the weak and the strong braid test. The ideal level should be around 40 parts per million. However, in this sample, we have 90 parts per million in the weak braid test and 126 parts per million in the strong braid test, which is extremely high. When phosphorus levels become too high, they can actually turn toxic for plants and prevent other mineral nutrients from being properly absorbed. Moving on to potassium. We have a level of 160 parts per million, which is close to normal. Ideally, the maximum should be around 150 parts per million. But because everything else in this soil is out of balance, this level is considered high. Moving on, we have magnesium. In this clay soil, the magnesium level is 502 parts per million, when it should be around 200 parts per million. Magnesium is one of those minerals that can make the soil very tight, hard, and extremely dense. For whatever reason, a high magnesium level tend to create highly compacted soils. Then we move on to calcium. Although 1,413 parts per million might seem like a high number, ideally it should be at least at 2,000 parts per million. Calcium is beneficial for the soil because it makes it a little softer and also supports the living organisms in the soil. Next, we have sodium. Sodium in high amounts can be toxic not only to plants, but even to humans. In this sample, the sodium level is 138 parts per million, when the maximum should be around 50 parts per million. So it's almost 3 times higher than it should be. That's one of the reasons plants do not perform very well in this kind of excess. Mythically, it is said that the Roman army salted their enemies' fields, which is untruth, as salt was part of their payment or salary. The term salting the earth is a symbolic gesture, occasionally referenced in Eastern biblical texts, including the Old Testament, to illustrate God's power and the toxicity of salt in excess. When we look at the soil pH or potential hydrogen, we can see that it's at 7.4. A pH of 7.4 means the soil is alkaline. As we can see, it's fairly alkaline, and plant tends to struggle in alkaline soils because many nutrients become locked out and unavailable to them. So plants cannot absorb those nutrients. Moving on to the buffer index. The buffer index is what indicates the stability of the soil pH. It basically means the soil has enough reserves to absorb changes without the pH changing too quickly. A simple way to understand buffer index is to think of it like a bank account. If you have $10,000 at the bank and suddenly you get sick and you need to pay $5,000 to the hospital, it affects you, but you're still okay because you still have money left. But if you only have $5 in your bank account and suddenly you need to pay $5,000 to the hospital, then you have to borrow money and go into debt. The same thing happens with the soil. When the soil has little or no buffer index, like in this case, the pH can suddenly drop very low or rise very high because there is nothing there to stabilize it. The cation exchange capacity, or CEC, is the ability of the soil and its minerals to hold and exchange electrical charge nutrients. Plants absorb nutrients primarily as ions dissolve in water, meaning nutrients are taken up either as cations, that's positively charged ions, or anions, negatively charged ions, depending on the element. In this case, we have a value of 12.3, which is pretty good. This soil has lots of extremely small clay particles that carry a negative charge, and that means it has a good ability to hold and release positively charged nutrients. Soils with high cation exchange capacity, or CEC, hold fertilizers very well, while sandy soils with low CEC lose nutrients quickly. Quick note, clay soils are very greedy. While they do attract and hold positively charged nutrients, they don't release them very easily because soil compaction, poor drainage, high pH, plus plant roots are not able to easily penetrate clay soils. When we get to the soil-based saturation percentages, we can see that some elements are in excess. Potassium might still be within acceptable range, but magnesium is extremely high, and sodium is also very high. These two elements, sodium and magnesium, are the main ones that make the soil become very hard, tight, and compacted. In excess, they can also become toxic to plants. The soil-based saturation analysis helps us determine the proportion of soil nutrients like calcium, magnesium, potassium, and sodium relative to acidic elements like hydrogen. It is important to keep them in balance so one does not interfere with the other ones. Aluminum toxicity only becomes a problem in highly acidic soils below a pH of 5.5, where the aluminum becomes soluble and causes phytotoxicity, that is, stunted root growth, poor nutrient uptake, and tissue death. As for hydrogen, because the soil is so alkaline, there is very little hydrogen present. A high pH or potential hydrogen means that the soil has a high potential to absorb hydrogen, but is lacking hydrogen. A low soil pH means the soil has already absorbed lots of hydrogen. If we were to measure the pH of pure sulfuric acid, it will be 0 because it cannot absorb or dissolve any more hydrogen. Quick note, I have been told that I have a very high PW, or potential wealth. In the meantime, I'm still broke. Nitrogen. We only have 2 parts per million of nitrogen, when ideally it should be between 10 to 15 parts per million. Lack of nitrogen shows as yellow leaf in most plants. Then we move down to sulfur. Sulfur is beneficial for plants because it helps with many important plant functions. In this case, we have 9 parts per million, which is fairly low. Next, we move on to zinc, which is another important micronutrient. Here we have 1.2 parts per million, and ideally it should be between 1 to 3 parts per million to maintain a good balance. Manganese. Don't confuse it with magnesium. Manganese is another important micronutrient. Ideally, we should have between 10 and 25 parts per million. But in this case, we only have 2 parts per million, which is very low. The next one is iron. Iron is at 24 parts per million. A good range is between 10 and 50 parts per million, but alkaline soils block iron from plants. Copper. Copper is at 0.8 parts per million, when ideally it should be between 1 and 3 parts per million. Copper is another one of those micronutrients that plants need in small amounts in order to properly carry out their functions. Next, we have boron. In this sample, we have 0.4 parts per million, when it should be between 0.5 and 1 parts per million. So we're below the ideal range. Then we have the excess lime rate. Since this soil is low in calcium, it has a low excess lime rating. Having a low excess lime rating is good because lime raises soil pH and blocks nutrients from the plants. The same goes for soluble salts. When we talk about soluble salts, we're not necessarily talking about sodium. Soluble salts are done by the reaction between an acid and an alkali compound. Even fertilizers are considered salts, and they are the main cause of soil contamination. Besides all this testing, it is a good idea to get to know your soils very well. In my case, what I do is I collect buckets of soils from most places I work and bring them home, where I can keep testing and see how they react under different wetness conditions. See how the pH changes, the type of gases or smells they produce, and the microbial activity under those conditions. So now that we have seen the soil analysis, let's see what the plant analysis looks like. Here we have a plant tissue analysis that was also done at Midwest Laboratories. And while in the soil, we do have very high levels of almost everything except organic matter, when we move to the plant itself, we see a completely different story. This sample was taken from a flax plant, Formium tenax, that was planted in this soil years ago. First, we have nitrogen. In the test results, we have 0.63%, when ideally it should be between 1.5 and 4.4% nitrogen. So this is not even half of the necessary nitrogen for the plant. Then we move to phosphorus, which we actually have an excess in the soil, but because it is blocked by other minerals, the plant is still highly deficient at 0.09%, when ideally it should be between 0.15 and 0.40%. Potassium. Potassium is also low. Normally, it should be between 1.5 and 3.5%, but here we only have 0.79% of potassium. Next is magnesium. Even though we have tons of magnesium in the soil, the plant should have between 0.2 and 0.4%, but here we only have 0.09% in the plant. Then we move to calcium. Just like humans need calcium for good bones, plants need calcium too. It should be between 0.5 and 1.4%, and here we only have 0.55%, which is on the low side. Moving on to sulfur. It should be between 0.2 and 0.45%, but in this case, we only have 0.06%, although sulfur was already somewhat low in the soil sample, is even lower here in the plant tissue analysis. Now we come to sodium. That's one element we definitely have lots of. Sodium should normally be between 0.01 and 0.3%. But here we have 0.317%, which is many times higher than what it should be. Moving on to iron. Iron should normally be 85 parts per million, but in this case, we only have 38 parts per million, which is very low from what it should be. Next is manganese. It should be 50 parts per million, but we only have 13 parts per million. Boron should be 20 parts per million, and we only have 13 parts per million. One interesting thing I have noticed is that plants within the higher limits of boron are not disturbed or eaten as much by deer. Copper should be 7 parts per million, but we only have 3 parts per million, which is very low. Zinc should be 35 parts per million, and we only have 20 parts per million. So once again, we can see in the soil, everything is present in extremely high amounts, many times higher than what it should be. But when we look at the plants, we see that they're actually starving. They are deficient in almost all the important nutrients. Now, let's take a look at the well water we're using for irrigation. This water analysis was done by Monterey Bay Analytical Services Laboratories a year before the soil analysis. But once again, we can see that many things are out of balance. Let's start with the anion-cation balance. We have a value of -4, which is actually okay. The cation-anion balance refers to the positive and negative charge elements in the water and how they balance each other out. In this case, the positive and negative charges seem to be relatively balanced, which is a good sign. Next, we move on to the total dissolved solids, or specific electrical conductance. That one doesn't really matter too much in this case, because it mainly tells us how many dissolved minerals are dissolved in the water and their electrical conductance. It is supposed to be around 0.55, and here we have 0.59. So that's acceptable and not really a concern. Then we move on to boron. We have 1.2 parts per million, or milligrams per liter, when the maximum should normally be between 0 and 0.5 parts per million. So we have way too much boron. Now let's look at the calcium in the water. Calcium is actually beneficial, and here we have a level of 49 parts per million, which falls within the ideal range of 20 to 60 parts per million. So that is good. Next is copper. Copper was not detected in the water, but ideally, well water should contain around 0.2 to 1 parts per million, because plants do need copper in small amounts. Then we move on to water hardness. Water hardness refers to how much mineral scale or scale buildup the water can create over time. It tells you the amount of minerals that are present in the water. In this case, we have a value of 212 parts per million, when ideally it should be between 0 and 200 parts per million maximum. Excessive hardness can stunt plant development by causing nutrient leakout, elevating the soil pH to undesirable alkaline level, and leaving crusty mineral buildup that stresses the root system. Under the right conditions, many of these minerals can actually become nutrients and food for the plants, as long as everything stays in balance. Now, moving on to iron. In the water, we have 608 parts per million, which is pretty high. If we look back at the soil samples, we can see that it's already a lot of iron in the soil. Ideally, a good balance will be around 100 to 200 parts per million maximum. So 608 parts per million is definitely excessive. Next is magnesium. We also have dissolved magnesium in the water. In this case, we have 21.6 parts per million, while the ideal range should be between 10 and 30 parts per million. So this level is not excessively high. Now, moving on to manganese. In the water, we have 57 parts per million of manganese, which is considered high. Ideally, it should be between 0 and 40 parts per million maximum. Next is potassium. Potassium should normally be between 10 and 20 parts per million. And in this case, we have 18.2 parts per million, which is good. Potassium dissolved in water can be beneficial because potassium is an important plant nutrient. Now let's look at silica. Silica is one of those micronutrients that can benefit plants. And because of the soil conditions in this well water, we have a level of 65 parts per million, when ideally it should be between 20 and 50 parts per million maximum. Next is sodium. In the water, sodium is at 248 parts per million, when it should be no higher than 50 parts per million. And remember, in excess, sodium is toxic to plants, sodium is toxic to humans, and in high amounts, sodium is harmful to most living things. Next is zinc. Zinc was not detected. And again, zinc is one of those essential micronutrients that plants need in small quantities. Ideally, it should be between 0 and 2 parts per million. Now we move on to arsenic. We are not too concerned about arsenic on this case because it is at 4.9 parts per million and the acceptable range is 0 to 10 parts per million. So arsenic is within balance. Then we have cadmium. Cadmium is at 0.4 parts per million, which still considered acceptable because the maximum is 0.5 parts per million. So is still within a manageable range. Next is chromium. We have a level of 2.2 parts per million, which is okay since the acceptable range is between 0 and 30 parts per million. So chromium is fine in the water. Lead was not detected, which is good because we definitely don't want any lead in the water. We move on to chloride. Chloride or chlorine in small amounts is actually essential for plants. In this case, we have 168 parts per million. Since this is well water, this is not like domestic city water where the water company adds large amounts of chlorine and other chemicals to the water. Chloride is a natural occurring element found in many places, and here we have 168 parts per million, which is a little high because ideally it should be between 70 and 140 parts per million maximum. Chlorine is part of chlorophyll, so plants use it in the process of making chlorophyll. Next is fluoride. We have 0.1 parts per million, which is fine because the acceptable range is between 0 and 0.5 parts per million maximum. Then we move on to nitrates. None was detected. Nitrates are usually remnants of fertilizers, and because this is well water and there are now fertilizers leaching into the groundwater, none were detected. The same goes for nitrite, none detected. Orthophosphate was also not detected, even though a range between 0 and 10 parts per million is considered tolerable. Having none detected is perfectly okay. Next is sulfate. In the water, we have 122 parts per million, which is within a good range since anything between 0 and 150 parts per million is considered acceptable. Then we move on to total alkalinity, which is basically the calcium carbonate dissolved in the water. In this case, it's pretty high. We have 470 parts per million, when ideally it would be better to have between 50 and 150 parts per million. This is bicarbonate dissolved in the water, and this one is also high. We have 573 parts per million, when a good range will normally be between 90 and 150 parts per million maximum. High bicarbonate levels lack the uptake of iron, zinc, manganese, and phosphorus to the plants. That is part why plants are deficient in these elements. After that, we have several other tests used for quality control, and overall, those results are actually pretty good. The pH of the water tested in the laboratory was at 7.9. And that's mainly because the water contains large amounts of dissolved calcium carbonate. Finally, sulfide was not detected in the analysis. However, because of the presence of iron sulfide and sulfur-reducing bacteria, when the water stays inside the hose for several days, it comes out with a strong rotten egg smell. That's exactly why understanding water chemistry is so important. I had a very sad experience at another property where we drilled a well. I strongly recommended drilling deep into the granite formation, but unfortunately, the client chose a different drilling company than what I had suggested. We had specified and gotten permits for drilling to 700 feet. But they stopped drilling at 380 feet as soon as they found water. The water already had a very strong rotten egg smell from the beginning. What made the situation even more concerning was the location of the well. It was drilled directly below an area where there once had been a beautiful garden from the mid-1950s through the late 1970s. Back then, people commonly used large amounts of chemicals and pesticides that today are known to be highly carcinogenic. Originally, the water was only intended for irrigation, so it didn't seem like a major issue at first. But later, the owner decided to switch completely from city water to well water for his home use. He loved his water, and he used it for drinking, cooking, and bathing every day. When I discovered he was drinking the well water, I strongly advised him to at least install a reverse osmosis filtration system. In the irrigation water analysis, we had already found very high calcium levels, and in agriculture, calcium we commonly use to help clean soils because many contaminants and toxins bind to the calcium and move deeper into the ground. Around the same time, his wife mentioned that her most recent blood analysis also showed a high calcium levels. That immediately became a cause of concern, and at my own expense, I decided to send the water for additional testing for volatile organic compounds, or VOCs. The results came back below allowable limits or not detected. Sadly, not long after, both of them developed cancer. He continued drinking his well water until the very last day of his life. Eventually, he passed away suffering from 3 different types of cancer. I am not saying that the water was definitely the cause, but experiences like this reminds us why soil analysis, plant analysis, and especially water analysis are so critical. Water can appear clean, clear, and even taste acceptable in certain categories, but that doesn't always mean it's safe over the long term. That's why understanding the full chemistry and history of the soil and water source is absolutely essential. So now that we have done the soil, plant, and water analysis, let's look at the ground structure. I also have the well drilling report from when the well was drilled. From the surface down to about 3 feet, we have brown clay. This is material that has broken down over thousands of years. Below that, from 3 to 40 feet, we have golden decomposed granite, or golden DG. This is a softer material that forms from golden granite before it fully turns into clay. Golden granite, through acidity, time, and decomposition, gradually turns into decomposed granite and eventually into clay. We use decomposed granite a lot in the landscaping, and if it's not too decomposed, it can be used as a base rock, like what you see on highways, roads, driveways, and even walkways. The finer material is often used around homes for landscaping, walkways, and decorative areas. Below that, from 40 to 100 feet, we have gravel with clay. Like I said, these come from larger granite pieces as they decompose. From 100 to 270 feet, we have tan clay with sand and gravel in different proportions. Then from 270 to 375 feet, we have limestone. This could come from old sediments or mineral accumulation. Limestone is one of the things that makes our water alkaline. Going deeper, from 375 feet to 440 feet, we have tan sand. This sand comes from golden granite that has broken down and settled over time. From 340 to 460 feet, we have sand with small gravel, which is part of the aquifer system. That's how the ground holds water, through layers of sand and gravel, and that's where we found most of the water. From 460 to 480 feet, we have tan sand, which is the finer material. From 480 to 510 feet, we have gray sand. That is from gray granite. It does hold water, but because it's much denser, is not the best water holding layer. From 510 to 515, there is a hard layer. From 515 to 680 feet, we have gray sand. Then from 685 to 700 feet, which is the deepest they drill, we have hard sandstone. When sand becomes compacted over time, it eventually turns into rock. That's what sandstone is. So that's what we have underneath this clay soil. Interesting fact, when this well was drilled back in 2005, it was producing 18 gallons of water per minute and stayed that way for many years. Most of the water begins its journey about a mile up the hill, where a low area forms a seasonal lake during the rainy season. Between that area and this well, there is a large property where the homeowner began rototilling the land for no apparent reason. Ever since then, this well has started producing less and less water. This is a perfect example of how leaving the soil, native plants, and grasses undisturbed allows rainwater to slowly soak into the ground and recharge the ground aquifers naturally. When the soil is repeatedly rototilled and disturbed, it becomes compacted and damaged over time. Instead of absorbing the water, the land begins shedding it across the surface, causing erosion, loss of topsoil, and contamination runoff. Healthy soil is not just dirt. It's a living sponge that protects our groundwater and our future.